Greg, you're right. It is August. It is vacation season, and if you're smart, you've been out of Austin for a couple months now, since it's 104 every day and the rain stopped months ago. So such is life. So we'll get started here. Thanks folks for jumping on. Hopefully we'll get a few more. We're going to talk about SE2050 today, and actually a special thanks, I'd say, to Swarna, who is our resident structural engineer. And she has, I know, sort of put out feelers on this and sort of worked this one through just with her involvement at SE2050 and probably possessing a little more knowledge than Greg and I, perhaps being a structural engineer herself. So we have two speakers today, and I think we're going to get an update on SE2050 and where we are and what's going on, and then a little bit more on some of the tools and some of the things that a little bit deeper into what's happening at SE2050 and maybe a little bit about the future. We have from 12 to 1 Central here. I know, Fraser, you said you might have to jump off, if I remember correctly, which is fine. We can hang around for a little bit after that. I think we tell speakers we might push closer to 1:30, but we do want to get folks out on time if need be at 1. So Annabel Shephard is with us, and she'll speak first. I'll do a slight introduction of you and Fraser. I'm not great at these. I know you guys gave me some notes, which is great, but Annabel works for PCS Structural Solutions, and I know you're involved at a structural engineering firm, right? And you're involved in a lot of the sustainability work that they do. You've been a member of, sort of involved with SE2050 since the beginning, right? And are on the SEI Sustainability Committee since 2019, which is fantastic. And I think you're a program mechanics lead at SE2050, so you can tell us exactly what that is. And then after that, we'll jump to Fraser Reid, works for Buro Happold in New York, has done 15 years there. So I'm sure you know a ton of ins and outs of Buro Happold, and has been involved in SE2050 for a long time. And I know you do some work in the benchmarking and essentially, reducing embodied carbon at Buro Happold and the structural work that they do. So some great folks here to talk about SE2050. And again, normal Zoom rules, y'all feel free. We'll sort of monitor the chat and we'll kind of let folks talk. But if something urgent comes to mind, feel free to unmute. If not, we'll do questions at the end, and I think everyone has sharing privileges, so feel free to pull up some slides and give it a go. And I think Annabel, we'll start with you.
Wonderful. Well, thank you so much, Thomas, for that introduction.
Yeah, absolutely.
I'll get my slides going here. All right, can everyone see my screen okay?
Yes.
Yep.
Perfect. Okay. So I'm going to kick us off by talking about SE2050 very briefly. My presentation is split into 3 parts. I'm going to give a brief background on the program. I'm going to discuss the program updates, what we're working on right now. And then at the end, I'm going to do a look forward and discuss where we see the program going. So with that being said, SE2050 was founded in 2020. I've included our mission on this slide for everyone to read. Essentially, we were founded with the goal of ensuring that there was a feasible pathway to net zero embodied carbon in structural materials by 2050. And we aim to provide a framework for structural engineers who want to reach that goal. Officially, we're a working group of the SEI Sustainability Committee, and we were approved by SEI's Board of Governors formally in 2019. Okay. So now to discuss a few updates on the program, starting with how our signatory firms have contributed to what we are doing. We currently have 128 structural engineering firms in North America signed on to the program. And of those firms, we have over 400 projects that have been submitted to our database, and we've received 135 embodied carbon action plans, or abbreviated as ECAPs, which is essentially the roadmap that each signatory firm creates, describing their goals and their progress towards net zero. So having spoken on the contributions signatories have made, We as SE2050 are continually updating our resources and information that we provide to our firms. And two things that we've published this year are, one, the 2023 Program Mechanics Guidance document, which provides more clarity on the requirements for the program, and our 2022 annual report, which is a document that we publish every year that gives an overview of what we've worked on. Additionally, we have quarterly signatory calls where we listen to our signatory firms and we incorporate the feedback that they give us. And we had a major program shift this year that's being implemented as we speak, where initially we started the program in order to simplify things for the firms that signed on by assigning folks due date for all their requirements based on the date that they signed on. And we received feedback that this was confusing and hard to keep track of. And so we're now implementing a collective due date that is similar to AIA 2030 that'll be in place by next March. And this is with the goal of improving the clarity of the program for the firms participating and creating a sense of community. And we're hoping that it'll be a little more straightforward moving forward. Okay, so now looking forward, I'm going to talk about looking forward for the database, for program mechanics, and then just very generally for the program. So starting with the database, just as an intro, the reason that we ask firms to submit projects to the database is so that we can develop benchmarks or target embodied carbon values for buildings. As structural designers, we have an understanding of how factors such as seismic design category, soil bearing pressure, and risk category can influence the cost of a structure, but these factors also can impact embodied carbon. So to make a successful comparison, we need to be gathering all of this data. We also need to know how our buildings are performing to keep us on track for net zero. So as we start to accumulate more data, trends can start to be spotted. For example, we can put together an ideal range of embodied carbon for timber versus concrete structures of the same scale. And before SE2050, there was no equivalent database that tracked structural embodied carbon or any of this information. And we're actively working to fill this void by collecting the data to better inform our industry in these critical next few decades. So in conclusion, from the data that we've collected so far, it is too early to draw any conclusions from that data. There's a high amount of variability for two major reasons. First, there's variability because there's no LCA methodology standardization. And second, there's variability because even in similar buildings, we can have wildly different structural designs. And so our priority moving forward is collecting more high quality data, more data period, and creating a standardized LCA procedure. Okay, so now looking forward on program requirements. This is a plot of 2020 to 2050 of the yearly design target for structural embodied carbon compared to structural embodied carbon in kilograms per CO2 equivalent. The red dot is October 2020. This represents when the program was founded. We created these requirements in October of 2020 with the goal of bringing everyone to the table. And so we set the bar very low. In order to reach our goal by 2050, we need to start ramping those program requirements up. And this is going to be a challenging process. It's going to occur gradually, but we've been working to make this process as easy as possible for signatories. And this includes, we drafted a pathway to zero this past year, and we're going to be implementing those changes to our requirements in the near future, coupled with resources to support firms as they continue that journey. And to close, I'm just going to go over looking forward, generally speaking, for the program as a whole. In January, we performed a detailed planning session as a team, and we determined that the following new programs are going to be incorporated into our work as a component of supporting the firms, as I was discussing under program mechanics. And this includes a recognition program to aid in a formation of a community by increasing the visibility and awareness of other firms that are working on the program with you, and through the creation of a little friendly competition. This also includes a mentorship program with the hope of facilitating communication, resource sharing, and general support between participants. additional priorities that we have for the end of this year and going forward are database updates to meet those priorities that I discussed earlier, as well as expansion of the ESIDs that we provide currently on our website. These are tools to help improve professional fluency in embodied carbon metrics. Updates to our ecom tool, which is our very simplistic LCA tool that we provide for free on our website. And then expanding educational outreach by doing seminars such as these, be able to talk to people directly and answer their questions, as well as educational outreach in the form of different kinds of documents. Specifically, we identified the need for guidance on structural material quantities and LCA methodologies. And with that, I come to the end of my time. Anybody have any questions?
Annabelle, I have some questions, but we can also hold off as well. If anyone else does or has anything pressing, feel free. But I could probably wait on mine. I'm just intrigued on some of the LCA stuff that you all have going on, and we're Perkins and Will is doing some internal LCA benchmarking as we speak.
Oh, nice.
And it is very interesting on the way different people do tally and the way I've done tally, having done it for many years versus others. Not saying my way is better. It might be worse, but we're figuring that out through how things work. But I might have a couple of questions on those when we close. But if
Wonderful.
no one else has anything, we can kick it over to Fraser, who's going to go a little more in depth, I think, into some of the things going on SE2050.
Okay, I'll unmute myself.
There we go.
Hi, everyone. Thanks for having me, and thanks, Annabelle. So what I'm going to share with you is a project I've been leading within SE2050 to provide better resources relating to design guidance for structural engineers. I can provide some more context, but brief personal introduction. I'm based in New York City. I co-lead our structural engineering team here in the city with Buro Happold. Originally worked in our London office. I've been in New York now for about 9 years. And the sort of subcommittee I'm involved with SE2050 is the resources subcommittee. So the goal of that group is to provide mostly sort of website resources that are accessible to publicly, but also to SE2050 signatories. So this is new content. It's a project we've sort of been working on for the best part of the last year and just released to our website a couple of weeks ago. So this presentation hasn't been given before. It was finished around about 11 o'clock last night, so bear with me if there's any typos, etc. Also would welcome any feedback afterwards, and we'll continue to kind of improve this information. So an agenda of what's in the deck, basically some background on the design guidance project and why it's important and where the guidance lives. And then go into some of basically a presentation version of the guidance and the content. So this is kind of how it's broken down: build less, build smart, evaluating design methods, implementing circular design principles, build light, be inquisitive. So in some ways, kind of a hierarchy of the different stages you go through in design. So very early on through, once you've selected your systems, how to refine them and reduce material quantities later on during design. So there's kind of a stage-by-stage logic to this, but with all things, it's not quite that simple. So these are the sections, and I'll just go through these one by one. Learning objectives, again, tied to the content here, but learning more about the resources available generally to structural engineers on the website, learning about the time-dependent nature of design decisions, how early decisions can make the most significant impact, learning about the importance of evaluating methods that are used during structural design and criteria that are set, used to develop the design, and the importance of those relating to embodied carbon reductions, and then learning tactics to reduce the embodied carbon on different framing systems. So introduction, this is a white paper that's also available on the website, but as Annabel explained, the mission of SE2050 is to provide a pathway towards net zero embodied carbon emissions in structures by 2050. And the most common question there is, how is that even possible? Because fundamentally, you know, structures have a lot of materials. Current methods of manufacturing require extraction of virgin materials, and emissions are kind of just part of the process. So how is this even possible? There's also a growing demand for buildings. So wherever we stand now is projected to increase over time. But ultimately, so this is Mark Webster's white paper. Ultimately, there are 4 different tracks that are necessary to eliminate embodied carbon in structural systems. The first is the design track, and that's really kind of what I'm focused on today, is in the way that we design structures. So being lean, reducing our demand for materials in the first place, is the first track. Then there is, I'm going to shift, that's the blue one. Then the orange is basically a clean electrical grid. So how materials are manufactured, less reliance on fossil fuels, and more reliance on green energy and electrical production. The third track is material production. So basically cleaning up the way that materials are produced, period. So you know, there's all sorts of research going into different structural materials, concrete, steel, timber, to from a material standpoint. The SE2050 website does also have specification guidance for structural engineers. So once you've determined you need a certain amount of materials, how to manufacture the materials that you do need as carbon efficiently as possible. And then the last track is the offsets track. So, you know, carbon's emissions are part of the game with material production. So basically reducing those insofar as possible and offsetting the remainder is really how to get there. The most desirable track, and this kind of highlights the importance of the design guidance, is in what you see here is the fourth track, which is really where we want to be, is to eliminate demand for materials in the first place. So that is a heavy weighting on the design track and materials track and electrical clean grid track. The least desirable is the status quo, where okay, we'll reduce a little bit across the board and just deal with the rest in offsets. I think we're all engaged enough to recognize that offsets are not a silver bullet in our industry, nor any other, for achieving net zero carbon. The other kind of analogy here is the reduce, reuse, recycle little pyramid that everyone's familiar with. You know, when we're dealing with our garbage at home, and it's really kind of rewiring our mindset in the same way for buildings. So design is super important and should really be the first port of call to reduce the industry demand for materials, period, before we start talking about well, how to clean up concrete, etc. Well, the goal should really be to reduce the demand for the material in the first place. Just back to SE2050, similar to what Annabel was describing. So it's a two-way commitment, and our commitment to the industry is to provide the resources and support to the profession. So again, this is just a new resource that's available on the website. When you go to the SE2050 website, Swarna is actually one of our key people for organizing the website content. At the moment, there's a number of splash pages. Here's where you are. And the design guidance currently lives in the structural materials strategy, but this is being reorganized at the moment. But if you visit our website, this is what you will see. And this is the new design guidance page, which I think I have a little scroll through, little video here that just shows you how it's organized. So it's a lot of written content at the moment, which I think I hope we can improve over time and maybe have more pictures and diagrams showing what some of the written, just elaborating on the written content. So the goal, really, we're calling this design guidance volume 1.0 with the goal of improving it over time. And I'm very much an advocate for something is better than nothing. So providing design guidance to the entire industry on structural engineering is kind of an impossible task, because design by nature is not an exact science, and therefore distilling design guidance onto a website was just there's no way it would ever be a perfect process. So our goal was to get this first version out there, get as much feedback as we can, and just aim to improve this over time. So in the same way, this presentation, I think I'm looking at in the same way. So put it out there, see what people think, and we'll continue to expand on the resources that we have available over time. Okay, so getting into the content itself. So this is really just putting my my design guidance hat on, and this is, what are the big items for structural engineering, and this information and why I'm here is not really just relevant to structural engineers, because it's about design at large, and a lot of structural decisions are more often than not integral to architectural decisions that are being made and impact all sorts of other aspects of design. So first and foremost, and as I'm sure you understand, really the most important thing that we can do is just reduce demand for new virgin materials, period. So as it relates to design, build less is really a key message. This is projected global floor area growth that you may recognize, but we are building effectively a new New York City in the world every month for the next 30 years. That's just based on population growth and business as usual projections for new construction. And if you project embodied and operational emissions, embodied carbon through 2050 is projected in our industry to contribute approximately half of industry emissions. So a new New York City every month for the next 30 years. Let that sink in. So a key, just what's our role as designers, right? Because very often we're given a brief and we feel kind of helpless to challenge that brief, but there are moments, and the more we as an industry advocate for building reuse, I think the more impact we can have collectively. So what is the most impactful way we can build less? Well, it's to use the existing built assets that already exist. So, next time you're on a project and the brief is to demolish something that's already there and rebuild, challenge that decision. It may range from something very small to something very large. In this instance, this is one of our projects in Detroit, which is an existing building. Sometimes these, I mean, and I think this is an example of it. It's sort of a hypothetical comparison. Up top is basically a hypothetical scenario. In this instance, the client had no intention to demolish and rebuild the building, but I think it's important just for illustrating the impact of building reuse are these carbon avoided assessments. There's also the CARE tool that was recently released, open source, that you may be familiar with, which aims to do this as well, which is to provide very high level carbon avoided assessments for retrofit scenarios. So in this instance, this is the embodied carbon emissions for a new construction scenario, demolish and rebuild. What's not captured here is all the waste associated with demolition and other environmental impacts, noise, demand for water. And then below, it just shows you with in this particular project, this is from our Revit model. It shows you kind of the interventions that were made to enable this building to be reused, and the embodied emissions just based on the amount of stuff that's required to get there, or is just a fraction of the demolish and rebuild scenario. So I think presenting metrics like this in a sort of simplistic and digestible way to clients and doing this collectively in the industry is important. Build smart. So this is early on in design, and as this graph illustrates, the time-dependent nature of decisions. What are the decisions you're making right up front in the project? Well, I mentioned, do we build at all? Can we reuse what's already there? The impact of that level of decision making is just eclipses the impact that you can have once these decisions have already been made. Once you've got, we've got to build new a certain amount of program and floor area. Well, it's going to take a certain amount of embodied carbon to get there. But as I'll illustrate with some of these other early decision-making topics, there's a lot more you can do, should you recognize that new build is necessary for your project. So one of the most carbon intensive type of structures are deep basement structures. There's a lot of concrete often goes in the ground in foundations and substructure. Basically, it's somewhat exponential. The deeper you go with basement structures, the bigger everything needs to get, based on primarily hydrostatic pressures. Is linear with depth, and so there's a huge difference between a 3-story basement versus a 2, and again a huge difference between a 2 versus a 1. So can we reduce or eliminate the need for deep basement structures? Think about this as sort of value for we're all familiar with value for money, right? But think about it as value for carbon. You're getting a certain amount of square footage at your B2 level, but you're paying so much more in carbon to get there. So think about where you put your building on your site. Think about the need for basement structures and whether those can be, the demand for those can be reduced. Ground floor advantage. So this is about where you're going to put your stuff. You've got a swimming pool that needs to go in the building, or you've got a bunch of MRI machines or vibration sensitive equipment. Where are you going to put that? Well, with the heavily loaded stuff, basically the lower you can put it in your building, the more efficient it's going to be for structure. Obviously, it's the columns that are supporting, imagine your rooftop swimming pool, it's your columns and vertical structure, but it's also a huge impact on your lateral system, which is basically all the stuff resisting earthquake loads, because heavy loads basically mean high earthquake loads, and your bracing or your walls and foundations to support the building laterally can be reduced significantly by placing your heaviest loads near the bottom of the building. With vibration sensitive equipment, basically, if you do have highly sensitive equipment, putting those directly on ground is the best way to go, because the structure that's required to elevate highly sensitive equipment just ends up being low value for carbon. Floor-based studies. So usually when you're working with your structural engineer, you know, what you'll see coming out at SD stage is some initial base studies. We're comparing different structural systems, we're comparing different materials. This is, again, getting this right early on in your project, and carbon's really just another metric, right? We're used to comparing structural systems in terms of cost, constructability, speed of construction, all of these considerations that aren't going away and still are important to our clients, but using carbon as a metric to compare different structural systems as you're conducting base studies. So conduct those base studies, don't jump to conclusions during early design, and communicate the findings of your base studies as it relates to carbon. There's no one answer about, you know, this, you know, always use this system. I think the key thing is to evaluate based on your expected span conditions, etc., different system options, and compare them in terms of embodied carbon. But as a rule of thumb, typically lower span dimensions typically will give you a reduced embodied carbon intensity of your structure. There's also other kind of rules. I get that this is quite text heavy here, but using regular structural grids, so avoiding lots of irregular grids, and also avoiding excessively long spans. Long span structures, you know, typically are a lot more carbon intensive, and same for excessive cantilevers. Small amounts of cantilevers can actually be fairly efficient for structure, typically up to about a quarter of the backspan dimension. Consider composite and hybrid floor systems. So composite floors are basically, well, traditionally concrete formed on steel framing, but composite floors can exist, you know, between any two materials. The reason composite floor systems are more carbon efficient than non-composite systems is the interconnectivity between the framing and the floor deck. Basically, they act together, and that helps you reduce the weight of your framing. Alternative hybrid floor systems, the American Steel Institute just released a new design guide for hybrid timber floor systems on steel framing. This is an example of, there's so much carbon just locked up typically into the floor deck of structures, that if we can use timber as an alternate to concrete for floor systems, then we can go a long way to reducing embodied carbon of structure. Prefabrication and offsite construction. You might kind of, as when you see some of these design guidance items, some of these, when you're conducting your life cycle assessment and you're really evaluating how much material do I have, and what's the carbon factor from the EPD that I'm using to get to the whole carbon value. This is an example of where you don't necessarily get the reward for using a higher level of prefabrication, because typically it's a similar amount of stuff, but the benefits of prefabrication are some of the sort of hidden benefits, because the processing of these materials, there's a lot, you know, the more you can construct in factories, the less site waste you have. Sorry, where I am, there's a thunderstorm happening, so apologies if I get cut off. So prefabrication, lots of benefits of prefabrication, reducing waste, just less demand for materials, lower site emissions, and also more easily deconstructible, as well as other benefits to contractors and owners, like higher levels of tolerance and faster construction. This particular system is a Cree system, which is prefabricated timber. You see there, the columns are constructed as part of the facade panel, so it's all kind of one piece. So this is a system that we've used in our Europe offices that we're kind of trying to bring over to the States. Lots of text here, so I'll try and abbreviate, but some recommendations as it relates to coordination. So avoiding, you're not always able to eliminate these types of things, but at least considering them during design and recognizing the carbon impact of some of these. So inefficient load paths, staggered column plans requiring lots of transfers, for multi-story buildings. Orienting your this is sort of good design practice that is illustrating that you can reduce embodied carbon through good design practice. So orienting your cores and considering how your MEP services are getting in and out, so you don't need to kind of brute force your lateral system. For floor framing, castellated, so integrating your MEP into your floor framing gives you additional depth on structure, so you can be more efficient with structure and more efficient overall. If you've got a stick-built system, not just using your stick-built elements for walls, but also utilizing them for gravity support, and some other, I think I'll move on, but some other suggestions there. Now getting into, this is maybe more nerdy structural topics, but this is some guidance for the processes that we go through typically as structural engineers and how to address some of these topics, because ultimately we have minimum code requirements which need to be met, but more often than not there's also other considerations that go into basically how we design and size structural members. So evaluate your loading criteria, use minimum code requirements where you can. Often on projects, there's custom loads that are stipulated to us by the client. I want a 250 PSF lab floor because I want to put my heavy lab equipment wherever I can in future. So interrogate those criteria, because it really is pretty linear. If you've got a 250 PSF live load versus a 50 PSF live load, you still have other structural loads to consider, but you're going to be 3 or 4 times as much structure needed to get there. So communicating that to your client and helping them understand the impact of custom loading requirements as it relates to carbon. Utilizing live load reduction provisions in code, basically within certain thresholds. It's recognized that if you have, a floor that's designed for 50 PSF or 80 PSF, the larger that floor is, the less likely that load is applied over that entire area. So there's provisions in the code that allow you to reduce live loads. So being cognizant of those and making sure you're making use of them. Mechanical equipment, often engineers will apply sort of generalized assumptions early in design that will get carried through. So there's a big design impact of considering the actual weight versus those generalized assumptions. Wind tunnel testing is a basis where you can reduce the code. Allows a reduction by up to 20% if you use a wind tunnel test, and the wind tunnel tests can show that in some cases wind loads are increased, but more often than not usually decreased versus kind of relatively conservative code assumptions. So consider wind tunnel testing, particularly for sort of specialist or tall buildings structures where wind tunnel is likely to control the design. If you can reduce your wind loads by 20% for a tall building, you're going to reduce your foundations significantly, and the thickness of your core walls and everything else. So in the same vein, serviceability criteria. So sort of structural engineering 101, serviceability criteria is everything other than strength. So strength is life safety. Structures are designed for a suitably low, basically a suitably low risk of failure, which basically means they don't fail under the prescribed structural loads. But more often than not, what controls design are actually your non-strength based criteria. How much is it going to deflect? What is the vibration performance? Are people going to be comfortable in the space? And the building code provides limits that we have to use for serviceability. It's just really important that when it comes to serviceability, engineers are realistic with these criteria, not prescribing unrealistic serviceability limits. And it comes down to modeling of structural models as well that often have assumptions built into models, that just to be cognizant of all of those. So taking advantage, this is the table from the building code, but you'll see that, for instance, roof members have a higher deflection limit, and making use of those. Generally, that's indicative of the fact that visually, if you see a roof deflect by a certain amount, you might not notice it, or if you do notice it, people are generally comfortable with it. Or if a floor is supporting non-brittle finishes versus brittle finishes, then we can accept higher levels of deflection. When it comes to vibration, it's really a question of really engaging in a dialogue with the team and making sure that the vibration requirements are appropriate. For sensitive equipment, the code provides various vibration limits, and often a client wants the highest performance, but they don't want to pay to get there, and using carbon as an additional means of dialogue addressing some of these topics is really the key thing, and engaging in that dialogue. Maximize design utilization. This is to a certain extent, I'm sure we'll give this presentation and there will be fairly consistent feedback. Well, this is just doing your job, and you might say the same for the previous couple of slides. But the iStruct have published a couple of papers that indicate that typically, looking at structures that have been designed and constructed in situ, typically structures are performing at around about 0.8 of their actual capacity, which indicates that we're kind of leaving 20% out there in the tank. And in some cases, design utilization is even lower. So there's lots of reasons why this happens through the structural design process, and just being aware of what those reasons are, and really setting a culture in the industry of reducing sort of layers of conservatism that lead to design utilization well below 1.0. Examples of that would be rationalization instead of optimization. And what I mean by that is, well, I've got a whole bay of beams that are all similar but slightly different, so I'm going to design the worst case of those, and I'm going to use the same beam size for all the others. Well, in doing that, you might have some beams that range, from fully utilized to 70 or 60%. In other cases, methods like that are compounded with, well, we're at DD stage, and I'm going to leave a 10% in there just to let things change, and maybe that 10% doesn't get taken back out of design, and the thing gets constructed, and safety factors that are all in good faith can compound, and suddenly this is how these things kind of build up. Also, so the application of material strengths, recognizing whether your design is going to be of a particular element controlled by strength criteria or controlled by serviceability criteria. Typically, lower strength materials have lower associated embodied carbon. So if you have a serviceability controlled structure, then it's appropriate to use lower strength materials. But there's no one size fits all, and really the important thing is evaluating this trade-off on a case-by-case basis. And as this diagram shows, it's about the design process. We're all thinking about this balance between cost, time, and quality. Well, I've got a deadline in 2 weeks, and I need to provide a safe structural design. So therefore, I might use some rationalization methods instead of optimization methods. And it's just adding another, well, what about the carbon impact of the processes we're using and the decisions we're making? We have software available now as structural engineers that can make it a lot easier to design, with computer models, structures that are, with the same amount of time, design structures that are less rationalized and more optimized. And a bit more on optimization. There's different types of optimization, so recognizing these. Size optimization is kind of what this diagram here is illustrating, but using software to set all your criteria in advance, and then when you run it, it should be fairly automated, and you should be able to sort of fully utilize every member. Shape optimization is where you're actually varying the size of your members along their length to where the demand is. And in a similar vein, topology optimization, if you have a truss structure or bridge structure or something of large scale, this method is often used, and it's it can be computer simulated these days to help you understand where the depth and what is needed and what the optimal sort of configuration of your structure is. So different types of optimization. And again, there's trade-offs and anticipating these trade-offs and recognizing carbon as a design, an equal design consideration to cost and constructability and all these other things that we're used to talking about. Implementing circular design principles. So I'm sure you're all familiar with the definition of the circular economy, but basically avoiding the linear process that the industry is currently, for the most part, set up with, where we take stuff out the ground, we use it, and then we put it in landfill or in where we're able to, we recycle some of those materials. So, for instance, a lot of steel material is recycled. That's a good example of kind of closing the loop there, and that's what we're talking about with the circular economy is, in the same way we're used to recycling our garbage and reusing something before it even becomes garbage, and treating building materials in the same way. So what are the benefits? Well, reduced extraction of virgin materials, reduced upfront emissions, and reduced waste. But what can we do now is really the question. So with structures, and some of these are challenging at the moment because the industry is not set up to do some of this at scale. But we influence demand, right? So if we as designers are advocating and seeking opportunities to incorporate salvage materials onto our projects, we have the ability to drive demand in the market at large. So salvage materials, there's really no reason we can't be reusing a lot of structural elements that are typically, as buildings are demolished, there's a push for deconstruction versus demolition. And, certain cities and states are adopting deconstruction policy. There's really no reason, if we take buildings apart carefully, that, many structural members can be reused elsewhere. So that's obviously a lower emission process than having to, with steel, for instance, melting it back down and recycling it. So if your project has an existing building that needs to be removed, that presents an opportunity to talk with your client about, well, can I reduce find that sweet spot. Can I reduce your cost as well as reduce your environmental impact if we can reuse some of the materials that are there for you already? Supply chains don't, you know, they exist to a small extent, but not at scale for kind of salvaged materials. But specifying these can help change that. So think about steel framing and timber beams. They're you know, commonly and quite easily tested for strength and applicability, so they can be reused fairly easily. Design for adaptability and deconstruction. This is, maybe you don't get the benefit in your life cycle assessment now, but what you're doing is enabling you know, someone down the road to take your building more easily apart and reuse the components that you've used. So it's reducing future economic incentives to demolish a building. So what can we do now? Again, is the question. I want, you know, real advice. What can I do now? Well, in some ways, it's actually like really basic stuff. So ensuring really good record information, so that basically your bill of materials that exists within your project, it's easy in future for someone down the road to interpret those and identify what can be reused. Simplifying connections so that they're more easily, you can take them apart more easily, using standardized elements and grids. Eliminating secondary finishes, you know, we're not suddenly encasing everything in concrete so that it's impossible to reuse it. In a similar vein, dry connections, so bolted type connections, mechanical fasteners, instead of welds and adhesives that you really, you know, they're a barrier in future to deconstructing. Modular construction can improve this. Talk to your manufacturers about how to certify their products and provide labels on components with strength characteristics. This happens on wood framing, but we don't really do it for example, steel framing. The images here, this one is a sort of innovative, more easily deconstructible steel connection system that's trademarked. And then typically if we're doing composite design, I talked about composite design earlier and the benefits of it, but typically that's achieved with welded shear studs that are then cast in place with the concrete. Well, you can't deconstruct that. So this is an example of a clamped system that, again, to achieve that connectivity between the two materials that's needed in order for them to behave compositely, doing it in a way that's more easily deconstructible. So I hope that we really see a lot of change in the industry around adaptability and deconstruction going forward. Okay, so you know you need a structure, and you know you're gonna build it from sort of one of your available structural materials. What are you going to do? So a slide here for the main structural materials that we're all familiar using: steel, concrete, and wood. One of our group members, Max Puchtel, is an AISC industry expert that's shared. You know, these are the high-level notes, but go on the guidance if you're interested in learning more about these topics. But with steel, involve your fabricator early. You know, they can really help you determine how to get the most out of steel and how to be efficient. There's different grades and strengths of steel available, so using those in a conscious way. Load optimized members, so putting the depth and the stiffness and the strength where it's really needed. Castellated beams, that's really, you know, it's a very low waste method to increase depth of structure and integrate structure with mechanical services. Utilizing camber. Camber is basically where you bend all your beams upwards before you use them, and this is an example of if service, you know, deflection performance is controlling the design. Well, adding camber, it doesn't add any more material, and it can take out some of that initial deflection and save you a lot of weight on structural framing down the line. And address fireproofing. This is important because we as structural engineers often evaluate one structural system versus another, and we kind of draw the line there, and we say we're not, well, we're not doing the whole building life cycle assessment, we're just comparing the structural systems. But with steel framing, usually fireproofing is basically spray on cement, or it's a cementitious spray that is pretty carbon intensive, and considering the impact of the fireproofing in your decision making when you're selecting your structural system, there are much lower carbon alternates to cementitious fireproofing. So consider those and just consider it as part of your decision making process. Build light with concrete. This is about being basically as material efficient as you can with a concrete structure. So there's various systems available, but before you even get there, the simple message is not all concrete is made equal. So carefully consider your concrete strength and mix selection. Basically, the vast majority of embodied carbon emissions for concrete come from cement production. Sort of 90% of concrete carbon emissions come from cement production. Higher strength concrete mixes require higher portions of cement and are therefore higher and higher embodied carbon. So, and then if you consider cement replacement materials, which is less about design guidance and more about how you specify your concrete, but you can have concrete mixes that vary enormously with their embodied carbon impact. So not all concrete is made equal. And then with your actual system selection, so really the best place to focus on with concrete frame buildings is the floor system. Concrete is a heavy material, and therefore when you have longer span floor systems, concrete can, just the weight of the structure itself ultimately can, it's often higher than your live load requirement, which is all your people and everything that your structure is actually supporting doesn't weigh as much as the structure itself because concrete is so heavy. So being efficient with your floor system, using depths that are appropriate, and incorporating deeper systems, lower weight systems are really the best way of reducing embodied carbon for concrete buildings. So waffle slabs, rib slabs, voided slabs, which is casting bubbles into the slabs, which take out weight of concrete where it's really not helping you with structure in the middle. It's the just basic kind of structural mechanics, is it's the stuff at the top and the bottom of your section that's doing the most work. And then post-tensioning, that's a way of introducing upward forces and pre-compression to structure that, typically post-tension slabs can be sort of roughly sort of 60% the thickness of cast in place without post-tensioning. And similarly for precast systems, using pre-stressed hollow core, that's similar to the bubble deck. You're just taking out the weight of the concrete where it's not really helping you with precast systems. And then don't forget about the impact of your steel reinforcing, which is, can be sort of 10 or 20% of the total with a concrete structure. And considering high strength reinforcement and mechanical coupling, because typically the way, when one reinforcing bar meets another reinforcing bar, they're lapped, so they overlap, and that depending on the size of the bar, your lap might need to be several feet. So that's just several feet of more reinforcing that's not really helping. So mechanical coupling devices, those laps can be replaced by screw details, and you can reduce your overall reinforcing quantity. With wood, not a lot to say about wood, but wood is obviously a very it's very different to steel and concrete because it's naturally occurring material, and there's carbon that is sequestered. But this slide is really, if you're using wood, how to use wood as efficiently as you can, because carbon sequestration can basically give you the impression that if I construct a wood building, so I've chopped down a bunch of trees, but look at all the carbon that's been sequestered, hey, my building is carbon negative now because I've used more and more trees. While the message on wood is still using less wood is better. So regardless of your sequestration, just use systems that use less materials. So with wood, again, similar to other materials, lighter weight, deeper systems. And then there's other recommendations on the website with some of these other systems. I think I'm probably at risk of taking too long. So this is the final slide, which is just hopefully a kind of call to action, but be inquisitive. And this is all about, there's no one size fits all with any of this stuff. Just be aware of the levers that you have and the decisions that you're making, and be as transparent as you can, and communicate the impact of these decisions with your project team and with your client. So try and be efficient in the way you do that as well. Early during design, use kind of rules of thumb and approximate methods to illustrate impacts on embodied carbon. There's a big difference between reusing this bit of the building and not reusing it. So we don't need to get bogged down into 3 weeks worth of life cycle assessment to tell a client that this is going to be good. Be ambitious, advocate for embodied carbon in decision making. And then last point, rapid progress here is only going to be possible if we share knowledge and good stories, bad stories, just stories at all, and lessons learned about these issues. And this can be done, within your own organization, within the CLF, or within SE2050. And so the dialogue is always welcome. So that's the end of my deck. I hope you maybe learned one or two things in that very information-heavy presentation.
I thought it was great, Fraser. Thanks. There is a lot of information, but I think that's good. I think it probably works for folks on this call for sure. And I appreciate the sort of obviously structural engineering direction of that, and I think that just with structural engineers I've worked with, just these discussions would be hugely helpful. Not that folks don't sort of know it, but being reminded of exactly that, just being inquisitive about everything we're doing. And we preach the same thing on the architectural side as well. So just digging as deep as we can on this stuff. We started a little bit late, so the timing's about perfect here. I know we're a little bit over, but I don't know if anyone had any questions. Is Annabel, are you still here? Are you one of the CLFs here on the you are great.
I'm here.
Okay.
Hello.
Okay, excellent. Sorry, I couldn't remember. You are a CLF. We have multiple CLF sign-ins here. So any questions from anyone? I think we heard a lot, but anything generated? No takers?
If nothing comes to your mind now, we're very responsive to our email, which you can find access to on our website. We have a whole team of people that would love to chat about SE2050 with you.
Absolutely. And there's more. We just got right into it here, obviously, but if there's any interest in joining, I know you can find all that. I've worked through a lot of AIA 2030 challenge presentations over the years, so I kind of know that if there's any resistance to joining, I know their descriptions, and you can get in touch about what's expected and what those commitments mean. And I know the 2030 sort of operational carbon's the same. I see a hand up, Mark Ledger. Feel free, sir.
Yeah.
Hey.
Hi, this is Mark from Austin Energy Green Building. Appreciate the presentations and the civil heavy, structural heavy content. I always learned from that, so I appreciate that. I'm just curious about some of those early design decisions that one can make on a project, and thinking about building owners, like what are the I don't know, persuasive arguments that work with them? You had kind of mentioned some cost savings associated with reusing buildings. Like, is that anything that's enticing enough to get new building owners to take that path? Or I don't know, what are some of the convincing arguments you've seen that have convinced owners to reuse buildings instead of building new?
Yeah, I'll give you maybe my position or kind of stance or experience on this. Like I think this is kind of a, something we all kind of recognize as consultants is, well, we would love for all of our clients to be super engaged and asking, for our advice on how to, reduce or just, from a sustainability standpoint, make our buildings as high performance as possible. We would love all our clients to be as engaged as we would like to be on our projects. But often, it's very much like, no, we need to highlight and make you aware of some of these topics that you may not already have been aware of. And in doing that, you kind of, I think, can help influence awareness and trends over time. I think on a single project basis, we do live in a world where the most effective means for implementing change is trying to find those sweet spots of reduced cost and reduced carbon, and also like doing that, but also sharing stories where that is where you have proven that to be the case. Because this, like, good practice with reduced embodied carbon, in structural engineering or anywhere really, is about being more material efficient. And in doing so, it should be common sense that we're reducing cost. So to me, it's about recalibrating what we recognize as good, what good looks like. And, historically, we've celebrated buildings that, might be kind of long span or really high flexibility, but the carbon impacts of that haven't really been measured or addressed. And there's been a cost discussion there about, okay, I've got a 100-foot span, but I'm willing to pay for it because look how cool this space is, or look how few columns I have and I can do whatever I want in this space. But we as an industry kind of need to be recalibrating that and recognizing that no, like, efficient span buildings are good practice, and this is what good looks like, and they also come at lower cost. So it shouldn't be as difficult a conversation as maybe we feel like it is sometimes with our clients.
That's it. We run into that a lot too, obviously, Mark, on the architectural side. And Fraser, I really like that sort of recalibrating what good looks like. I talk to a lot of consultants and a lot of folks, and I'm trying to push an idea of like performance precedence in a sense, which is like, you have precedence, which in our world, honestly, like, push toward aesthetics, right? I mean, you have a program and you have a function, you pull some aesthetic ideas in, and that really gets people going. And I'm more and more of the mind of like, let's put precedents up there for performance reasons, right? And whether that's embodied carbon, operational carbon, whatever it is, sort of, it's really about the story you tell and about what you show. And if you sort of pick the wrong things to show out of the gate, you can really influence people early on and in some roads that we might not want to go down. So even with mechanical consultants, I'm always saying, okay, bring your precedents to the table. What good things have you done? Show us as a group, and let's talk about those as precedents, and again, sort of changing that norm of what good looks like. So I appreciate that. There was a comment in the chat, Michael Donahue, appreciated, absolutely, an article in Nature in UK, carbon cost of global wood harvest calling into question some of the total carbon sequestration and what that means. And I do know that's true to some extent. I haven't read that article, but I do know that we sort of talk about good wood and bad wood. And, you know, having gone to forestry school myself, although I was spent a lot more time at the architecture school. But that said, there's good forest management, there's bad forest management. And I know if you're in the latter, you can really torpedo some of the good things that you can have from sort of responsible sourcing of wood. And you know, the article might go to some other places, but I do know that can be a serious issue. And so the point of less is more, even in the wood world, is important. And something to be said, you know, Fraser, I really love the sort of hybrid opportunities that you brought up too, right? Which is something that's really interesting to me, and I haven't seen it a ton, you know, happening. But again, you know, we're in Austin and we have some great things going, and folks from AEGB here. But that said, I know our clientele can sometimes shift still pretty far away from the bleeding edge. So I haven't been involved with that as much in mass timber or in sort of convincing people to go there with us. But certainly hybrid structures is really intriguing. And, you know, I know just from doing 1 million LCAs, if those slab numbers, if that 6-inch concrete slab, and then, you know, oops, we pulled the columns in and we got a cantilever, so now they're 8-inch concrete slabs. Don't worry about it. I know that can make a huge difference. So some of those ideas are really intriguing.
I would also add that it's a way of taking some of the fear factor out of using mass timber. Is if you go hybrid, then it's a way of maybe introducing it in a way that it's, you know, timber's being priced out a bit in the market at the moment, that you really have to have a client that wants it in order to design in timber, because the demand is going up so much that it's not as, or at least in my experience, not performing from a kind of cost standpoint where we would like to see it. So it's a way of reducing kind of the, you know, we don't need an all mass timber building. We can use it on these high impact like floor slabs, and we're going to get a big carbon saving from it. But you know, you're not building your whole building from timber. And in the same vein, there's composite timber concrete systems, and this is an evolving market. But another big concern with timber buildings is timber is, you know, a combustible material, and there's building code limits, all with good reason, about how tall you can build, and different jurisdictions will have their own take on building code requirements. But building compositely, where you have kind of concrete floor decks with timber framing, really at that point you've got a totally different fire scenario and fire separation between floors, and yeah, there are other benefits of hybrid construction as it, you know, relates to fire protection issues and risk issues that on a real project are really real considerations, and can often be barriers to innovating and using more innovative systems.
Yeah, absolutely. Okay, I think we're about at time here. I'll plug clfatx.com, folks. We don't have a ton of people on the call. You all probably know this, but just in case, there is a website, and we are on LinkedIn as well. And I think we post about, you can sign up for sort of postings about events there. And I think we've probably got a couple more months, and we'll have something else out here. Annabel and Fraser, thank you both so much for jumping on with us. And obviously SE2050.org, right? That's the spot. Easy to find for everyone. And Greg and Swarna, anything else, feel free.
I think this was great. Thank you so much both for preparing this deck. Really helpful.
Thanks for setting it up.
Thanks to both of our speakers and all the great questions and conversation.
Enjoy your weekends.
Yeah.
Thanks, everybody.
Thanks, everyone. See ya.
Bye.
Thank you.